In this screencast, I'll briefly discuss Ampere's law and then show you a problem related to your homework. Ampere's law basically states that the curl of B is proportional to the current density, and if we basically take some current distribution and we enclose it by a surface, basically we can calculate the total I. So if I add up all the J enclosed by a surface that I draw, that would be the I enclosed by that surface that I draw. If I take you're taking the flux of the curl here, this is basically adding up all the flux of the curl by Stokes' theorem. That's the same as just adding up all the vector along the edges of that surface. Okay, so if you draw a surface, you could add up all the flux through it, all the flux of the curl through it, or instead the shortcut is just to add up the vector along the edges. That's Stokes' theorem. And if we draw some surface around and enclose some kind of current distribution, and I add up all of the volume current density in that surface, then I will get the enclosed current. So this is similar, this is analogous to Gauss's law, where now instead of drawing a Gaussian surface, you're drawing an Amperian loop. And so once again, we assume that for the Amperian loop, we have to draw a loop in such a way that the B field along that path is equal. So instead of the E field along that surface being equal at every point, now it's the B field, the magnetic field, along that path is equal at every point, and they have to be parallel to each other. Just like before, for Gauss's law, E had to be perpendicular to the surface. Now it's parallel to a path. So I just drew this. This is my own notation. This dl hat. So the B field is going to be in the direction of the Amperian loop if you draw it correctly, such that the B field is equal and always in that direction. So again, with these problems, you have to know a lot about the problem before you start. But this is our spherical horse. We can actually get a lot out of real life problems by taking these assumptions. Let's do an example. In this problem, what I have is a fat wire, and I have current running from top to bottom. And what I'm interested in doing is I want to draw an Amperian loop where I'm interested in calculating the magnetic field. So where do I want to calculate the magnetic field? For this problem, you're going to do it inside and outside for your homework. Let's do the outside part together. So I'm interested in a point P, the outside one. Oh, that's fine. We'll have blue. That's all right. There's point P. And now I need to draw an Amperian loop that goes through that point such that the magnetic field is equal on this Amperian loop. That loop also has to catch, it's basically kind of like my flux catcher, it has to catch all the current flowing through this fat wire. So let's draw that. It's basically the best Amperian loop to draw here is a disk. Okay, and we'll assume that that's centered, and then my loop here is going to be a radius s. Alright, so basically if I want to find my dl integral here, right, this is basically what's the length of the path that I drew. So here's my path, and what it's doing is it's catching all the current through this wire, and I'm assuming that my magnetic field, this is the assumption I have to make, is equal all along this path. So I have to know something about the problem. That would also assume, because I've chosen this path, that would also assume that the magnetic field is in this direction. And this one's not too... We began this unit talking about how point your thumb in the direction of current flow and the magnetic field is going to circulate in the curl of your fingers. So this seems reasonable that the magnetic field should be in the phi hat direction here. And I should add that here. Let's do dl hat. Alright, so what we should have here is mu naught I inc. Ooh, that's supposed to be an inc. It's going to be in the phi hat direction. And the integral is just going to be 2 pi s. That's the circumference of this loop that I drew. Now, we need to find out what I inc is. Because I'm on the outside, I could actually say this is I total. That's like we said Q total before. So I could be done here. It's going to be equal to mu naught I total. Because I'm enclosing the total current on this thing. 2 pi s phi hat. However, if you want to do the integral, and you would have to do it if it's inside, we need to know something about j. And so we should say that j is constant in this problem. Let's keep it easy. And so if we want to find I enclosed, what we need to do is we need to integrate j over the dA here. Alright, the dA is going to be the area of that loop that I drew. So in a sense I drew a surface, and my surface is also has a boundary. So my surface is this disk. That's the surface I'm integrating over here. And my loop is just the boundary of this. So what we find out is all the current is just up until, well, let's give this fat wire a radius. Let's call it radius A. That has a radius A. And so my integral here, if I integrate all the way out to the edge of my loop, it's kind of silly because there's no current being caught through this part. So really I only need to integrate out to the edge here. So my integral is going to be, we said J is constant. So J is just going to be J in whatever vector direction. We can write that down. Let's write down J vector is going to be equal to J z hat. Okay, dA, the direction of dA here, is also going to be z hat. And so this integral, it's going to be in cylindrical coordinates. The J pulls out, and I'm going to get S ds d phi. And these are going to go, it's going to go 0 to A. Oops, there we go. And 0 to 2 pi. A little messy there, sorry. And basically we know that we're going to get the area of the disk of radius A. So this is going to be equal to pi A squared. Alright, let's box that off. So I total is fine in this case. So another way to write this is going to be equal to mu naught J. The pi's are going to cancel. I'm going to get an A squared phi hat, and then it's going to be over 2s. And I think we got that right. Yep, pi A squared. Good. So this is in terms of the volume current density. Both these answers are correct. This is just in terms of the volume current density, and this is in terms of I total. Now think about what happens. Remember these problems, Gauss's law, and it's true in Ampere's law. They come down to basically, do you know what I inc is or Q inc is? So if you draw a loop in the middle of that thing, you're not going to integrate all the way to A. What are you going to integrate instead? All right. And as it says in the homework, this particular problem mimics, not exactly the uniformly charged sphere that we did in electrostatics.